About 85% of all matter is unknown. It's all around us, but it seems to be barely noticeable. We've never detected it, it's uncharted territory. It's only when we looked up at the stars that we knew it must be there to hold the universe together the way that it is. This missing chunk is called dark matter. Scientists have built detectors to try and get a better idea of it. The main type of detector is essentially a big tank of a noble gas in its liquid form. So it's just a big collection of atoms that are cooled down to be kept as still as possible. So we can imagine this big tank of atoms as a crowd at a game of cricket or baseball, whatever you fancy, waiting for the ball to be hit into the crowd where maybe one of them will catch it. And this is sort of what's happening in these dark matter experiments. They are waiting for a dark matter particle to come into the detector and hit one of these atoms in the tank, causing what's called a nuclear recoil, where the nucleus of this atom gets bumped back by the collision. The detector can pick this up from the sort of ripple effect which follows on from this. So if you picture one person in our crowd catches the ball and they stagger back and the people around them have to move to get out of the way, then we get a ripple effect through the crowd. For dark matter though, this is a really rare event, and it's made even rarer because the dark matter particle has to be above a certain energy to create a big enough ripple for the detector to pick up. To try and improve their chances, scientists obviously want to make a more sensitive detector. One idea that has surfaced is based on what's called the Migdal effect. That's something predicted all the way back in 1939, but it's never actually been observed. The basic idea is that when a nuclear recoil happens, the nucleus of an atom moves, but the cloud of electrons will have a time delay as they try to catch up to it. The physicist Arkady Migdal found that because of this, there was a small chance that this will cause one of the electrons to be ejected. So we have the possibility of a dark matter particle hitting an atom and an electron is produced, which is great because we know how to detect that. But where this gets really exciting is that a dark matter particle could hit an atom in the detector, not with enough energy for that ripple effect to be registered by the detector, but it might still produce an electron through the Migdal effect. So that now opens up the range of dark matter particles we could detect by quite a bit. This idea naturally has gained a lot of attention with physicists, including some in STFC's particle physics department at the Rutherford Appleton Lab. As part of the Migdal collaboration, they came up with an experiment to observe the Migdal effect for the first time. It requires a particular type of neutron source, which should be fired at some target to cause nuclear recoil and hopefully observe the Migdal effect. Now, luckily, just over the road from the particle physics department is ISIS, a world-class neutron source. And a simple chat over a coffee between members of ISIS and the particle physics department found that a new project at ISIS would be exactly what was needed to test the Migdal effect. And so this chance conversation could lead to the first observation of this decades-old theory, which could in turn lead to the first direct detection of dark matter, taking us one step closer to learning the mysteries of the universe. It's a testament to the importance of collaboration and interaction within science.